Good morning, learners and viewers. Welcome to the session of Masters of Business Administration. Today we will be talking about project management, MMPO 002. In our last session, we were talking about Unit 5 that pertains to project network analysis CPM part, and we were talking about network analysis and rules of network construction. To continue with that, how the network is drawn and how the numbers or the numbering on the event is performed. Numbering the event is done by Fulkerson rule. Now the thing is that what rule is that? After the network is drawn in a logical sequence, every event is assigned a number. The number sequence must reflect the flow of the network. In numbering the events, the following rules should be observed. First, event number should be unique. Second one, event numbering should be carried out on a sequential basis from left to right. The initial event, which has all outgoing arrows with no incoming arrow, is numbered as 1. Delete all rows, arrows emerging from all the numbered events. This will create at least one new start event out of the preceding events. Numbering all new start events 2, 3, and so on. Repeat this process until all the terminal events without any successor activity is reached. Number the terminal node suitably. We have to note that the head of the arrow should always bear a number higher than the one assigned at the tail of the arrow. Now we will take a problem and we will try to understand how this is drawn. The problem is construct a network for each of the projects, being whose activities and their precedence relationships are given in this tabular form. The activities are from A to K, and the predecessor activities are shown in the table. Now, how this has to be processed and how this has to be drawn. Solution pertaining to this is we can see that A, B, and C are concurrent activities as they start simultaneously, and B becomes the producer of the activity E and F. Since the activities J and K have two preceding activities, dummy can be introduced if possible. We will see this if dummy actually is required at the end of the diagram. To start with, we will draw a circle. We can see over here that A, B, and C are the three events which are starting from it. That means the arrows will start, three arrows will start, and they will be numbered as A, B, and C. Then we will move to D. The predecessor to D activity is A. We will draw a circle at the head of A, and we will write D on the arrow. Now, we will move to E. We will see that E has two, E and F has two activities performed before it, that is B. So from B, we will mark two activities, E and F, and we will draw two circles at the arrow's head. Now, moving further, you can see that activity G and H is there. So activity G and H, G starts when C has completed. Now down that we can see that C is there, so we will move towards right and we will draw G over there with the arrow. Now we have reached F. F includes G and F. Moving further, now we will see to I. I has E with its at the back. So E will be connected with I, J and K are left. J and K have H and I with it. So we will be connecting J with H and I. That means at the top, J will start. And K will end up at F and G. F and G are at the bottom. So that means the third circle will be drawn and it will be having the activities of J and K. Now on the right, you can see that this is a complete diagram what we have achieved. Now we will be assigning the numbers to it. We started from the left one. That is first, moving towards A, that is 2, B is 3, C is 4. And moving further, as we made the diagram, so after 2 it will be 5, and between E and I, it will be 6, and 7 will be down, 8 will be up, and ninth will be the closest. This is finally what we have. Now, again, some terminologies which will be related to PERT, time analysis. Once the network of a project is constructed, the time analysis of the network becomes essential for planning the various activities of the project. An activity time is a forecast of the activity. An activity is expected to take from its starting point to its completion under normal conditions. So we should know different notations. These are the basic schedule for the required for the basic scheduling computation. Within brackets, it's written like this only. Within brackets, IJ's activity with tail event I and head event J. Tij is the estimated completion time of the activity Ij. Es is earliest starting time of the activity Ij. Ef is earliest finishing time of the activity Ij. Ls latest starting time of the activity Ij. And the last it is latest finishing time of activity Ij. The basic scheduling computation can be put under the following three categories. That means we have three steps how we can complete this. First one is forward pass computation. It is for earliest event time. Before starting computation, the occurrence time of the initial network event is fixed. The forward pass computation yields the earliest start and the earliest finish time for the activity Ij, and indirectly the earliest occurrence time for each activity. Computation begins from the start node and moves towards the end node. Let 0 be the starting time of the project. Second one, step 2 is earliest starting time, that is ESIJ, should be equal to EI, which is the earliest possible time when an activity can begin, assuming that all the predecessors are also started at their earliest starting time. Earliest finish time of the activity is the earliest starting time plus activity time. So mathematically we can write it as EFIJ is equal to ESIJ plus TIJ. Step 3 is earliest event time for event J is the maximum of the earliest finish time of the activity J. used for event only, whereas float is used for activities. There are mainly three kinds of float. First one is total float. It refers to the amount of time by which the completion of an activity would be delayed beyond the earliest expected completion time without affecting the overall project duration. Free float is the time by which the completion of an activity can be delayed beyond the earliest finish time without affecting the earliest start of a subsequent succeeding activity. And the third one is independent float, the amount of time by which the start of an event can be delayed without affecting the earliest start time of an immediately following activities, assuming that the preceding activity has finished at its latest finish time. So mathematically, we can say that total float is TFIJ is equal to latest start minus earliest start. Free float is, it is represented by FF, and it is the difference between EJ minus IJ and TIJ. And independent float is the difference between EJ minus LJ minus TIJ. Now we move to critical path method. Critical path method is a graphical technique for planning and scheduling of the project. This technique involves the preparation of the network in the form of arrow diagram, and its analysis is to indicate the critical path. It has the potential for scheduling of a task in minimum days and or cost in accordance with the specified constraints. The critical path is important as its length determines the minimum time required for the completion of the project. The initial path requires greater attention because of the following reasons. First one, the critical path highlights those activities which must be performed more rapidly if the total project completion time is to be reduced. Second one, any delay in activities which are on the critical path will produce delay in the completion of the project. That is, will postpone the final completion date of the project. On the other hand, delays in non-critical activities may not actually delay the completion of the project. And the third one is advanced planning and improvement along the critical path may cause another path to become critical. Now, we take a problem to understand what we said. A problem is related to a leather manufacturing company. It has to start the finished goods from the factory to the storehouse. The path from the factory to the storehouse is through certain intermediate stations as indicated in the following diagram. The company executive wants to identify the path with the shortest distance so as to minimize the transportation cost. And the problem is to achieve this objective. Now, this diagram is basically given to us. We can see that on the left side is the factory, that is, it has been numbered as 1. And there is a storehouse which is numbered at 6. And in between, we have some numbers written on the arrow, and there are some numbers which are written on the circles. Now, how to identify and what these numbers signify? We have to first of all calculate the shortest route. This is used to minimize the total distance from the node designated as the starting node or the origin to the another node designated as the final node. If we take an extreme left corner of your screen, we see that there is 1 to 2 and 1 to 3. Now, there is a number written on the arrow. That is, from 1 to 2 is just 40, and from 1 to 3 it is 100. We have to take the minimum one, and the minimum one is 40. That means our unit will be, movement will be from 1 to 2, and it has been marked red over there. Moving further, from 2, we can see on the diagram there are three events which are occurring: 2 to 3, 2 to 4, and 2 to 5. That means we have to calculate, we have to analyze the minimum distance in units. We can see from 2 to 3 it is 35, from 2 to 5 it is 65, and from 2 to 4 it is 95. And from 1 to 3 it is 100. The minimum one is 2 to 3. That means we will mark 2 to 3. Now, how much distance we have traveled? We have traveled 40 plus 35. That is why it is marked 75 over there, the bottom. Moving further, now we are at 3. From 3, we can see that there are two events from 2 to 5 and from 3 to 5. If we talk about the minimum, it is 20, which is from 3 to 5. That means straight away we will be discarding the root 2 to 5 and we will be adding 20 to it to 75. That means we have reached station 5, and that is the total distance has been traveled is 95. So now our path is from 1 to 2, 2 to 3, 3 to 5. Now we move to 6. When we move to 6, we can see over there are two parts, and these numbers are same. But confusion arises why we have left 4, 6, and we are considering 5, 6. Numbers are same, but if we go back to the initial part, we find that earlier stations were having maximum number, maximum units. So that is why we will be closing this from 5 to 6, and the total note 6, and the total distance which has been traveled is 135. 95 plus 40. That means the critical path of this problem is from 1 to 2, 2 to 3, 3 to 5, 5 to 6. And the distance is 135 units. Now we will be considering different other aspects. Going further, we will be talking now in terms of program evaluation and review technique, which is part. Problem is the same problem. And now we are provided with optimistic time estimate, that is represented by TO, most likely time estimate, that is TM, and the pessimistic time estimate, that is TP. This again will be given to you in this tabular form. Now the thing is that what we are supposed to calculate. We have to find out the time actually required to complete the following project and the critical activities. Now, picking up this diagram, we will be using 3 given times, and we will be finding out that estimate time. Estimate time is basically calculated by the formula TO plus 4 times of TM plus TP whole divided by 6. So first of all, we will be calculating TO plus 4 TM plus TP for all the activities. So that means we get 24, 36, 60, 72, 54, 126, 132, 30, and 80. And in the last column, we will be dividing all these numbers by 6. We get 4, 6, 10, 12, 9, 21, 22, 5, 3. Now the thing is that what is the next step, what we have to do? Using the single time estimate of the activities, we have to draw a diagram. Activities are A to I, and the most likely time estimate is given to us. We have this particular diagram with us. Here we can see we have some idea of critical path method. First of all, initially keeping an eye on this diagram, we can find out 4 or 5 different ways of starting the event from 1 and ending up at 8. The first, what my consensus say, that is 1, 2, 3, 5, 6, and 8. Second one, 1, 2, 4, 5, 7, 8. These are the basics what we can do. Now furthermore, how we can change. Now the change can only be done in the last one. Now what will be that change? We will start it from 1, 2, 3, 5, 7, 8. And the other one will be 1, 2, 4, 5, 6, 8. That means we have 4 rows. We have drawn, we have 4 such loops. Now what to do? How to calculate the time? Taking the first loop, 1, 2, 3, 5, 6, 8. The loop has been marked with red and the respective times of the activity are summed up. So that means the total time for 1, 2, 3, 5, 6, 8 is 48 days. Similarly, for the second path, we have 1, 2, 4, 5, 7, 8, and the times is 4 plus 10 plus 9 plus 2 plus 3, which comes out to be 28 days. Third loop, it is 1, 2, 3, 5, 7, 8, and when we will be totaling up this time, this comes out to be 27 days. And the fourth loop, 1, 2, 4, 5, 6, 8. When we will be summing the time, it comes out to be 49 days. Now we have 4 loops, 4 days. How to find it out? Which is the most suitable time for the completion of the project. That means we have to consider the maximum time. Maximum time is for 1, 2, 4, 5, 6, 8, which is 49 days. That is the critical path. What are the critical activities? Critical activities are A, C, E, F, and H. Those activities which are not included in the path are non-critical activities, and that are B, D, G, and I. And the project length is 49 days. Now we have to calculate the standard deviation and variance of the critical activities. The diagram, CPM diagram is in front of you. The optimistic time, most likely time, and the pessimistic time is known to us. It was given. So we will be taking these values for our critical activities. That means critical activities A, it is moving from 1 to 2. Its optimistic time, pessimistic time, and the most likely time will be taken from the table. Similarly, for activity C, E, and F, and H, all these 5 activities, the table will be made. Now, what we have to find? We have to find the range. Range is TP minus TU. That means the difference between the pessimistic time and the optimistic time. Next step is to calculate the standard deviation. Standard deviation is TP minus TO divided by 6. It is calculated over here. Now comes the variance. Variance is denoted by sigma square, which is the square of the standard deviation. So we will be just squaring up all these numbers. Now, we have to calculate the variance of the project time. The last column will be summed up, which comes out to be 43 by 9 weeks. We have to calculate the standard deviation, that is the under root of variance, means under root of 49 by 43 by 9, which comes out to be 2.18 weeks. Now we take up another problem which will be related to flow and slack. The problem is given to us. Consider a project with the following details. We are given with 3 things only. That is the activities, producer activity, and the duration of the completion. We have to determine the earliest and the latest time, the total float of each activity, the critical activity, the slacks of the event, and the project completion time. That means we can say that this problem consists of everything what we have discussed or talked till now. Initially, we will be drawing the diagram. We have to first of all calculate. We have to draw the CPM diagram. The problem initially is given to you. We'll start with A. A, B, C, D are the three activities which are on it. That is, you can see from activity 2, we have to draw three events. That is 3, 4, and 5. At 5, we have producer as B, producer as F, C, G. And from 5, we are moving further to activity 6, and then 7 and 8. Now, on these numbers, you can see that there are some numbers which are written on it, on each activity. So we have to see two things, name of the activity and the duration of the, which is given in time. So we will be just placing all these numbers on this activities. For A, it is 8. For B, it is 13. For C, it is 9. For D, it is 12. For E, it is 14. For F, it is 8. For G, it is 7. For H, it is 12. For I, it is 9. For J, it is 10. And for K, it is 7. Now, we can see there are 7 paths. Which are these paths? From this, we have to calculate the time duration, and we have to consider the maximum time duration of the completion of the project. So first of all, we see that initially at the top, we can see that 1, 2, 3, 6, 7, 8, the simplest one. Second one is 1, 2, 5, 7, 8. Similarly, while we are drawing this path, we have to estimate the time. So we will be adding the time which is consumed for the completion of this sequence for A, B, F, J, K. We will be summing up 8 plus 13 plus 14 plus 10 plus 7, which comes out to be 52 weeks. So for the second path, 1, 2, 5, 7, 8, we get 33 weeks. The third path is 1, 2, 3, 5, 7, 8. For that, it comes out to be 45 weeks. The fourth one is 1, 2, 4, 5, 7, 8. For that, it comes out to be 43 weeks. The next one is 1, 2, 4, 5, 6, 7, 8. For that, it comes out to be 56 weeks. The next one is 1, 2, 3, 5, 6, 7, 8. For that, it comes out to be 58 weeks. And the last one is 1, 2, 5, 6, 7, 8, for which it comes out to be 46 weeks. The maximum time of the path is 58 weeks. Now, we have to calculate the earliest time, or the 3 times we have to calculate now from the problem. So we have the critical CPM method in front of you. The problem as it is has been taken. Now we will be moving from left to right. That means we are calculating earliest time of occurrence of node. From the one, it is 0, as it was told earlier that the initial time will be 0. At node 2, node 2 is basically time of node 1 plus the activity time of A. That is 0 plus 8. That means we can say that when we have reached activity 2, we have completed 8 weeks time. Now we move to node 3. Node 3 is basically completion of time node 2 plus the activity time, which comes out to be 8 plus 13. That comes out to be 21. Now we have reached node 3. At node 4 is basically node 2 plus the time of T. That comes out to be 8 plus 12, that is 20. Now, when we have reached 5, we have three activities being performed at node 5. That is 3 to 5, 2 to 5, and 4 to 5. So we have to calculate the time individually. That is 8 plus 9, 8, 21 plus 8, and 20 plus 7. We have to take maximum. That means on node 5, it is almost 29 weeks. Moving further to node 6, we have two activities over there. That is E and H. For E and H, for E it is 21 plus 14, the time, which comes out to 35. And at considering H there, that is 29 plus 12, which comes out to be 41. So we have to take the maximum. That means on event 6, 41 weeks have completed. When we move to node 7 has I and J with it. So for I, it is, when we are calculating for I, it is 29 for 5 plus 9. That comes out to be 38. And for if we are talking about 6 to 7, so it is 41 plus 10, which comes out to be 51. At 7, we have reached 57 weeks. And for the last, the node 8, 51 plus 7, which comes out to be 58. And the maximum time for the period is 58 weeks. That means earlier start time will be tabulated. What we have calculated earlier is being tabulated over here. That is TE. For each activity, it has to be written in the tabulated form, which comes out to be 0, 8, 8, 8, 21, 21, 20, 29, 29, 41, and 51. Moving further, now we will be moving from left to right now. We have to calculate backward pass. So that means we have the calculation of latest allowable time of occurrence of the event. Now, we will start with 8. That means here at that place, at that moment of time, we have 58 weeks with us. Moving backward, initially we will be subtracting only 7. That comes out to be 51. That means at node 7, we have 51. Now we will be moving from J2 we will move it to from 7 to 6. So if that comes out, we are talking about event 6, node 6. So node 6 will be 51 minus 10. That is straight away 41. Now at event 6, node 6, we have two activities. So we have to consider the time of node 6 minus the activity of H and the time of node 7 minus the activity of time I, which comes out to be 41 minus 12 and 51 minus 9. Here, when we are moving backwards, we have to calculate minimum one. The minimum is 29. That means here it comes out to be 29. For node 4, it will be node 5 minus activity of G, which is 29 minus 22, which is 29 minus 7, which is 22. Now, for node 3. Node 3, we can see that there are two activities, 5 and 6, which are happening. So that means we have to calculate the minimum time. So for node 5, it was 29, and for node F, it was 41. So we will be subtracting 8 and 14 respectively, which we get 21 and 27. We will be considering the minimum one, that is 21. Now, moving back, at node 2, at node 2, we have three activities being performed, 3, 5, 4. For that, we have to see what was the time node for 3, it was 21. What is the activity time of B, that is 13. Time for node 4 is 22, and time for activity D is 12, and time for node 5 is 29, and the time for activity C is 9. So we will be calculating all these three numbers. We get 8, 10, and 20. We have to consider only the minimum one, that is 8. And for node 1, it is 8 minus 8 is 0. That means here we can see that our calculation, what we have done, is correct. So similarly, we will be drawing another diagram which will be related to the latest finish time. That means for all activities in the reverse, 58, 51, 51, 41, 29, 29, 41, 22, 29, 41, and 8. Now, complete diagram is placed over. Activities, duration of week, earliest start time, earliest finish time, latest start time, and latest finish time. This is what we have tabulated. Now, to calculate the total float time, we have to see that we have to calculate the latest finish time minus the earliest finish time, which is in the tabular form. So here we can see for the first event it is 0, for the second one it is 0 again, for C it is 12, for D it is 2, for E it is 6, for F 0, G 2, H 0, I 13, and for J and K it is 0. Now we will be picking these values, the 0 one. Now it has been placed over here. That means the activities which are having with 0 float are A, B, F, H, J, and K. That means those activities which are without float are the critical activities. And the total project completion time is 58 weeks. Now, we take up another problem, which is how to calculate the slacks of the event. Slack of an event is the latest allowable time of occurrence of the event minus the earliest expected time of occurrence of that event. From that tabular diagram, we have just picked events, earliest expected time of occurrence, and latest allowable time of the event. And we have calculated the slack of the event. Here we can see that slack of the event for event number 4, which is 2. Now, what does we are going to interpret it from it? On the basis of the slack of the events, it is concluded that the occurrence of event 4 may be delayed up to a maximum period of 2 weeks, with no other event can be delayed. That means when we have reached activity 4, we can delay it. Delayed, we can wait for other events to be performed, rather moving to 5. We can move to 5. No doubt, when we are in actual circumstances, we move. But for another way, if we want to hold it, we can hold it, the event 4, for a period of 2 weeks. Now, we move to most important next part, that is crashing of a project. What does it mean? A process of shortening the time to complete a project is called crashing and is usually achieved by putting into service additional labor or machines to an activity or more activities. Crashing involves more cost. A project manager would like to speed up a project by spending as maximum extra cost as possible, minimum extra cost as possible. Project crashing seeks to minimize the extra cost for completion of a project before the stimulated time. What are the steps required or performed in project crashing? Assumption: it is assumed that there is a linear relationship between the time and cost. Let us consider project crashing by the critical path method. The following 4 steps are adopted. Step 1: find the critical path with the normal times and normal cost of the activities and identify the critical activities what we have done. Second, find out the crash cost per unit time for each activity in the network. This is calculated by means of the formula. The crash cost uh, per time period is crash cost minus normal cost upon normal time minus crash time. This is a standard formula what we will be using it. Step 3 is select an activity for crashing. The criteria for the selection is as follows. Select the activity on the critical path with the smallest crash cost per unit time. Crash this activity to the maximum units of time as permissible by the given data. Crashing of an activity requires extra amount to be spent. However, if the company is prepared to spend extra money, the activity time cannot be reduced beyond a certain limit in view of several other factors. The step 1, we have to note that reducing the time of an activity along the critical path alone will reduce the completion of the project. Because of this reason, we select an activity along the critical path for crashing. Step 3 is basically we have to consider the following questions. If we want to reduce the project completion time by 1 unit, which critical activity will involve the least additional cost? And on the basis of least additional cost, a critical activity is chosen for crashing. If there is a tie between the two activities, then any the tie can be resolved arbitrarily. It is the selection of the manager. Step 4, after crashing an activity, find out which is the critical path with the changed conditions. Sometimes a reduction in the time of an activity in the critical path may cause a non-critical path to become critical. If the critical path with which we started is still the longest path, then go to step 3. Otherwise, determine the new critical path and go to step 4. Step 3 again. Now we see how this can be performed with a practical example. A project has activities with the following normal and crash time and cost. All the things are given to us. We have to determine a crashing scheme for the above project so that the total project time is reduced by 3 weeks. Picking this, first of all, we have to draw the critical path diagram. Then we have to assign the normal time which is given in the problem. We start with, we have 8 activities over here and we have 2 paths for performing it. For the 2 paths, we have to calculate the time period. Picking up the first term at the top, 1, 2, 3, 5, 7, 8. The total time comes out to be 25 days. And path 2, that is 1, 2, 4, 6, 8, which comes out to be 20 days. Path 1 is the critical path, and the critical activities are A, C, E, G, and H. And the non-critical activities are B, D, and F. Given that the normal time of the activity is 4 weeks, while in crash time it is 3 weeks. Hence, the time of this activity can be reduced by 1 week if the management is prepared to spend an additional amount. However, the time cannot be reduced by more than 1 week, even if management may be prepared to spend more money. The normal cost of this activity is 8,000, whereas the crash cost is 9,000. That means a crushing activity A by 1 week will cost the management an extra amount of 1,000. Now we have calculated the time. What is the difference between the normal time and the crash time? For the activity 1, it is 1. For activity 2, it is 2. For three activity C and D, it is 1, and activity E, it is 2, and for the remaining F, G, and H, it is 1. Now we have to calculate the crash cost per unit time. That means we will be subtracting the crash cost minus normal cost, which comes out to the data is given on the right column. Now, what to do, how to proceed? A non-critical activity can be delayed without delaying the execution of the whole project. But if the critical activity is delayed, it will delay the whole project. Because of this reason, we have to select a critical activity for crashing. Here we have to choose one of the activities A, C, E, G, and H. The crash cost per unit time has been calculated, and for A it is 1000, for C it is 1000, for E 1000, and for G it is 6000, and lastly for H it is 3000. The maximum among them is 1000. So we have to choose an activity with 1000 as the crash cost per unit time. However, there is a tie between A, C, and E. The tie can be resolved arbitrarily. So we have selected A for crashing. We reduce the time of A by 1 week by spending an extra amount of rupees 1000. Now we can see that the original path has been changed. So from A to productivity time has been reduced by 1, so it has come now 3. We will again rework for the time, which comes out to be 24 weeks. And for part 2, it comes out to be 19 weeks. So here again, the maximum has to be taken, that is 24. Therefore, path 1 has been reduced by 1 for A cannot be reduced further. Therefore, we have to consider now C, either C, E, G, and H for crashing. Among C and E, which have at least cost per unit time, that is 1000, there is again a tie between C and E, which can be resolved arbitrarily. So we have taken C and we will be reducing it by 1 week. Now, this comes out to be C has been changed from 4 to 3. Again, we have to calculate the critical path, the time. Same calculation has to be done for path 1, we found out to be 23 weeks, and for path 2, we found out 19 weeks. Maximum is still 23. Therefore, path 1 has been reduced now. A or C cannot be reduced further. Now again we have left with E, G, and H. Among E, E has the least crash cost of unit time. We reduce the time of E by 1 week with an extra cost of 1000. From the given condition, we have reduced the project time by 3 weeks. Since this has accomplished, we stop this step over here and the results comes out to be, we have arrived to the following crashing scheme of the project. Reduce the time of A, C, and E by 1 week each. Project time after crashing is 23 weeks, and the extra amount what we have is required is 3000. Now we move to unit act, that is earned value analysis. Project managers use the earned value management approach to monitor how their projects are performing in comparison to project baselines. It is common to think for a project progress as being ahead of schedule, behind the schedule, or over budget. In this global era of highly competitive conditions, all the business practices operating in the public as well as in private sector are made to operate faster than even before. As a result, it is observed that industries are working on multiple projects simultaneously. To make these projects work, regardless of the scope, companies need skilled project managers. Project control is the activities conducted by the project manager within the horizon of monitoring and updating the project, which examines the current situation of the project and differentiates from the initial project plan to develop a current plan suiting the actual situations. Earned value analysis is a very much useful and efficient tool used widely. For the management of successful projects, project management presents several tools and techniques, of which earned value analysis is the most regarded one. It is a method used for measuring the performance project at any given point of time. A technique that uses work in progress, what we short call it as WIP, status to predict the future performance of the project. Earned value analysis is a method that allows measuring of the amount of work actually carried out on a project rather than the basic review of cost and schedule reports. EVA provides a method that combines a project domain and schedule under a bound together situation matrices to monitor and forecast the project's performance. A project manager is then able to use the progress meter to forecast a project's total cost and date of completion based on the trend analysis or applications of the project's burn rate. This method relies on a key measure known as project's earned value. Earned value is defined as the project cost of work performed. This helps the product managers to compute performance indices or burn rates for cost and schedule performance, providing information on how well the project is doing or being performed relative to its original plans. What are the different terms which are used in earned value analysis? Earned value analysis allows the project manager to answer the following three questions. Where have we been? Where are we now? And where we are going? In earned value analysis, unlike in traditional management, there are three data sources. The budget, which is a plan, value of the work schedule, that is in short we call it as PV. The actual cost value of the work completed, that is AC. We will be using these three terms later. First of all, what is planned value? It is the planned cost that has been estimated for the following project. PV explains how much the project was is supposed to be at any given point in the project schedule and cost estimate. Cost and schedule baseline refers to the physical work schedule and the approved budget to accomplish the scheduled work. PV can be looked in two ways, that is cumulative and the current. Cumulative is adding up all what we have concluded, and the current one is where we are. Cumulative PV is the sum of the approved budget for activities scheduled to be performed to date. Actual cost, that is AC, it is the total cost incurred directly or indirectly in completing a work on a particular project during a given period. This number tells us the amount has been spent and is with planned value can be looked in terms of cumulative and current. Cumulative AC is the sum of actual cost of activities performed to date. Current AC is the actual cost of the activities performed during a given period. Earned value. The third one is it is the estimated value of the work that has been actually completed. To understand the accomplishment of the project, EV is applied to the numbers and calculations in the project. EV basically quantifies the worth of the work done to date. EV can be represented in a cumulative and a current fashion as well. Cumulative EV is the sum of the budget of the activities accomplished to date. And current EV is the sum of the budget for the activities accomplished in a given period. From this diagram, we can see that when a cumulative diagram for the cumulative cost versus time is drawn, we have three terms: the actual cost, the planned value, and the earned value. They have been depicted by three different colors. Red one is for actual cost, blue one is for planned value, and green one is for the earned value. If a horizontal line is drawn from the top of the actual value cost intersecting the planned value and drawing another horizontal line which is joining the green line as well as the blue line, we have three regions A, B, and C. These regions depict three values of, that means, the current position of the project. Now, earned value and performance matrices. Cost variance, it is the difference between the earned value and the actual cost. That is CV is equal to EV minus AC. Sometimes it is also expressed as the difference of budgeted cost of work performed and the actual cost of the work performed. If the variance is zero, the project is on budget. Similarly, schedule variance as it expresses the difference between the work that is ahead or behind the plan and reflects a given measurement method. The formula utilizes to express schedule variance in project earned value minus the project planned value as on date of the estimation. That means SV is equal to EV minus PV. If the variance is zero, the project is on schedule. Schedule performance index, that is SPI, is the measure of schedule efficiency on a project. It is the ratio of earned value to the planned value. SPI is equal to earned value divided by planned value. If SPI is equal to or greater than 1, it indicates a favorable condition. And if the value is less than 1, it indicates an unfavorable condition. Cost Performance Index CPI. It is a measure of cost efficiency on a project. It is the ratio of earned value to actual cost. The CPI is equal to the earned value divided by the actual cost. CPI greater to or greater than 1 indicates a favorable condition and a value less than indicates an unfavorable condition. This is basically how it is related. This is the matrix. SPI is EV minus upon PV. CPI is EV minus AC. SV is EV minus PV. And CV is EV minus AC. But this is what is the relationship between all these terms. And graphically, we have earlier seen that now we are in this graph which is related to project cost and the time schedule. There are three different parts, that is the actual cost, the budget at completion, that is the and the earned value. When we are drawing this diagram, we can see the differences of the cost variance, schedule variance, and the data date. If, now what we conclude, if the value is greater than 1, over budget or behind schedule, and if it is less than 1, it is under budget or ahead of schedule. Now, the thing is that we have completed two blocks, and the critical part has been discussed today. That was how the CPM critical path method per and per diagram and its analysis. So with this, we will be concluding today's session. 59.